Consider what this means for the search for extraterrestrial life. If every black hole contains a universe, and if our universe alone contains millions of black holes just in our galaxy, then the number of potential habitats for life becomes truly staggering. We're not just looking for life on other planets in our universe. We're potentially part of an infinite community of consciousnesses distributed across countless levels of reality. Some might exist in universes nested within black holes in our cosmos. Others might exist in the parent universe that contains our black hole. Still others might exist in parallel universes nested within other black holes in that parent reality. The numbers are mind-boggling. Our Milky Way galaxy alone contains an estimated 100 million black holes. If each of these contains a universe, and if even a tiny fraction of those universes develop life, we're talking about billions of civilizations existing in realities nested within our cosmic neighborhood. And this is just within our single galaxy, in our single universe, at our single level of the hierarchy. Some of these nested civilizations might be far more ancient than our own. While our universe is 13.8 billion years old, the universes within the oldest black holes in our cosmos might have existed for even longer periods, having more time to develop complex forms of life and intelligence. They might have solved problems that we're only beginning to grapple with, developed technologies that we can't even imagine, reached levels of understanding about the nature of reality that make our current knowledge seem primitive. The Fermi paradox, the question of why we haven't encountered extraterrestrial intelligence despite the apparent likelihood of its existence, takes on new dimensions in this framework. Perhaps advanced civilizations don't communicate across space within a single universe. Perhaps they communicate across the levels of the hierarchy, finding ways to signal between nested realities. Think about the challenge of communication across the hierarchy. If time flows differently at each level, a signal sent from a parent universe might arrive in our reality at incomprehensible speeds, or conversely, a message we send might take eons to reach its destination from the perspective of the recipients. The physics of communication between nested realities would require technologies and concepts that we haven't even begun to develop. Perhaps what we interpret as mysterious phenomena in our universe, dark matter, dark energy, quantum entanglement, are actually the subtle influences of intelligences operating from other levels of the hierarchy. The parent universe above us or the nested universes below us might be trying to communicate, and we're only just beginning to develop the physics necessary to understand their signals. Dark matter, which makes up about 27% of our universe, interacts gravitationally but seems invisible to electromagnetic radiation. What if dark matter isn't matter at all, but rather the gravitational influence of structures in the parent universe? The massive galaxies and clusters in the reality above us might create gravitational fields that penetrate into our nested universe, manifesting as the mysterious dark matter we observe. Dark energy, the force driving the accelerating expansion of our universe, presents an even deeper mystery. In the nested universe model, this acceleration might be a consequence of our motion through the interior of the parent black hole. As we fall deeper toward the center, the geometry of space-time itself changes, creating the appearance of accelerating expansion from our perspective. Quantum entanglement, the spooky action at a distance that Einstein found so troubling, might be a manifestation of connections that span across the levels of the hierarchy. Particles that appear entangled in our universe might actually be connected through higher dimensional pathways that exist in the parent reality. The instantaneous correlations we observe might be shortcuts through the larger geometry of the nested structure. This possibility raises profound questions about consciousness itself. If our minds are patterns of information processing that emerged from the physical processes of our universe, and if our universe is nested within larger realities, then consciousness might be a fundamental feature that emerges at every level of the hierarchy. We might be conscious beings within the thoughts of larger conscious beings, while simultaneously containing conscious beings within our own physical processes. The neurons in your brain, operating according to quantum mechanical principles, might themselves be universes where consciousness emerges on scales we can't imagine. Your thoughts, your dreams, your memories might be the cosmic history of countless nested realities. Each one is real and meaningful to its inhabitants as our universe is to us. When you remember a childhood moment, you might be accessing a cosmic epoch in a universe nested within your neural pathways. When you imagine a possible future, you might be glimpsing the evolutionary possibilities of civilizations existing at quantum scales within your own consciousness. And conversely, our entire cosmic history might be a fleeting thought in the mind of a being whose consciousness operates on the scale of the parent universe. The 13.8 billion years from the Big Bang to the present might correspond to a few microseconds of contemplation in a mind so vast that galaxies are like synapses and black holes are like neural connections. This perspective doesn't diminish the meaning of our existence. It amplifies it infinitely. Every choice you make, every moment of beauty you experience, every act of love or creativity or discovery resonates not just through our universe but potentially through all the levels of reality connected to ours. Your life is not just a brief spark in one cosmos. It's a thread in an infinite tapestry of consciousness that spans all levels of existence, from the quantum to the cosmic to the hypercosmological scales we're only beginning to imagine. Every decision you make, every problem you solve, every insight you gain contributes to the evolution of consciousness itself across the entire hierarchy of nested realities. But let's return to the scientific evidence that supports this extraordinary vision. Recent observations from multiple sources are converging on conclusions that support the nested universe model. The JWST observations of cosmic asymmetry are just the beginning. Other telescopes are finding evidence of large-scale structure in the universe that shouldn't exist if the traditional Big Bang model were completely correct. The Planck satellite, which mapped the cosmic microwave background in exquisite detail, found anomalies that suggest our universe has preferred directions, cosmic axes that break the supposed symmetry of space itself. These anomalies align remarkably well with what we'd expect if our universe inherited angular momentum from a rotating parent black hole. One of the most intriguing anomalies is the so-called axis of evil, a mysterious alignment in the cosmic microwave background that seems to point toward specific directions in space. This alignment shouldn't exist in a truly isotropic universe, but it makes perfect sense if our universe retains a memory of the rotation of the black hole from which it was born. Meanwhile, advances in black hole physics have revealed that these objects are far more complex than we previously understood. The information paradox, the question of what happens to information that falls into a black hole, might be resolved if that information becomes the initial conditions for a new universe rather than being destroyed. Quantum mechanics tells us that information cannot be destroyed, only transformed. If matter falling into a black hole carries information, and if that matter becomes the seed for a new universe, then the information is preserved in the structure and evolution of that nested reality. The information doesn't disappear. It becomes the physics, the constants, the initial conditions of an entirely new cosmos. This insight connects the nested universe theory to some of the deepest questions in physics: the nature of information, the relationship between quantum mechanics and gravity, the origin of physical laws themselves. If our universe's physical constants, the strength of gravity, the charge of the electron, the speed of light, all emerged from the specific properties of the matter that collapsed to form our parent black hole, then these constants aren't arbitrary. They're determined by the physics of the parent universe, which in turn were determined by the physics of its parent universe, and so on infinitely upward through the hierarchy. This suggests that the laws of physics themselves might evolve across the levels of the hierarchy. Each nested universe might have slightly different constants, different forces, different possibilities for structure and complexity. Some might allow only simple atoms to form. Others might permit exotic forms of matter and energy that we can't even conceive of. In some nested universes, the electromagnetic force might be so strong that atoms could be the size of molecules in our reality, allowing for incredibly complex chemistry on scales we consider microscopic. In others, gravity might be so weak that planetary systems never form, leading to entirely different evolutionary pathways for matter and energy. Natural selection might operate not just on biological organisms within universes, but on the universes themselves. Those universes whose physical laws permit the formation of black holes will spawn new universes. Those that don't will remain childless branches in the cosmic tree. Over infinite time, the hierarchy might evolve toward universes that are increasingly capable of generating complexity, consciousness, and new levels of reality. We might be living in a universe that has been fine-tuned not by design, but by evolution, by the natural selection of physical laws across countless generations of nested realities. Our universe's apparent friendliness to life and consciousness might be the result of an evolutionary process operating on the grandest scale imaginable. This evolutionary perspective on physical laws provides a natural explanation for the anthropic principle, the observation that our universe's constants seem perfectly tuned for the emergence of complexity and life. We don't live in a fine-tuned universe by cosmic coincidence. We live in a universe that evolved the capacity for fine-tuning through the reproduction and selection of physical laws across the infinite hierarchy of nested realities. But what does this mean for our future, both as individuals and as a species? If the nested universe theory is correct, then our long-term destiny might not be extinction when our sun dies or when our universe reaches heat death. Instead, our future might lie in learning to navigate the hierarchy of realities, to communicate across levels, perhaps even to influence the formation of new universes nested within our own. Advanced civilizations in our universe might not focus on expanding across space within our single reality. They might focus on expanding across dimensions, learning to access and influence the parent universe above us or the nested universes below us. The ultimate frontier might not be outer space, but inner space, the infinite depths of reality that exist within every black hole, within every quantum process, within every moment of conscious experience. Instead of building starships to travel to distant galaxies, future humans might build consciousness ships to travel to distant levels of the hierarchy. Imagine technologies that could manipulate the formation of black holes, creating universes with specific properties designed to foster the emergence of consciousness and complexity. We might become gardeners of reality, planting seeds of new universes and nurturing their growth across cosmic time. Or consider the possibility of communication across the hierarchy. If we could learn to send signals through the quantum foam that connects different levels of reality, we might be able to communicate with our descendants in nested universes billions of years before they even exist from our perspective. We could leave messages for civilizations that won't evolve until long after our own universe has grown cold and dark. And if consciousness is truly a fundamental feature that emerges at every level of the hierarchy, then our development as conscious beings might be part of a larger evolutionary process that spans all levels of reality. Every moment of awareness, every insight, every act of understanding might contribute to the evolution of consciousness itself across the infinite hierarchy of nested universes. This vision transforms every aspect of human existence into something cosmically significant. Your thoughts, your relationships, your creative endeavors, your struggles and triumphs, all become part of the eternal evolution of consciousness across infinite levels of reality. You are not just a temporary arrangement of atoms in one small universe. You are a unique expression of the universe coming to know itself, and that universe is itself an expression of larger realities coming to know themselves in an endless hierarchy of awakening consciousness. Every scientific discovery, every work of art, every act of compassion, every moment of wonder contributes to the vast project of existence understanding itself. We are not separate from the cosmos. We are the cosmos becoming conscious of its own nature, and that consciousness extends infinitely upward and downward through all the levels of nested reality. Of course, the nested universe theory remains speculative. Like all revolutionary ideas in science, it must be tested against observation and experiment. The evidence we have so far is intriguing but not conclusive. The JWST observations of cosmic asymmetry, the anomalies in the cosmic microwave background, the puzzles about initial conditions and fine-tuning, all point towards something beyond the traditional Big Bang model, but they don't yet prove that we live inside a black hole. Future observations might provide more definitive evidence. If the theory is correct, we should be able to detect specific signatures in the cosmic microwave background, particular patterns in the distribution of galaxies, certain relationships between the rotation of our universe and the properties of black holes within it. We might even find ways to probe the boundaries of our nested reality, to detect signals from the parent universe or to communicate with the nested universes contained within our own black holes. Advanced gravitational wave detectors might pick up echoes from collisions in the parent reality. Precision measurements of fundamental constants might reveal tiny variations that betray our universe's nested origin. But regardless of whether the nested universe theory proves to be literally true, it serves a profound purpose in expanding our conception of what's possible. It challenges us to think beyond the boundaries of our everyday experience, to consider possibilities that are simultaneously rigorous in their physics and breathtaking in their implications. It reminds us that reality is likely far stranger and more wonderful than we can currently imagine. The universe we think we know, vast as it appears to us, might be just one level in an infinite hierarchy of realities, each one as real and meaningful as our own. We might be living inside a black hole, but if so, it's the most magnificent black hole imaginable, one that contains not crushing singularities but infinite possibilities for existence, consciousness, and meaning. It's a black hole that has given birth to galaxies and stars, to planets and life, to minds capable of contemplating their own cosmic origin and destiny. As we continue to explore the cosmos with our telescopes and our mathematics, with our spacecraft and our theories, we're not just mapping one universe. We might be beginning to chart the infinite hierarchy of nested realities that extends infinitely above us and infinitely below us, each level containing its own wonders, its own forms of life and consciousness, its own contributions to the eternal evolution of existence itself. The next time you look up at the night sky, remember that those stars and galaxies might be your fellow travelers on a journey through the interior of a cosmic black hole, all of us falling together through dimensions we can barely comprehend toward destinations that might be the big bangs of new universes waiting to be born. And the next time you contemplate the mystery of your own consciousness, remember that your awareness might be part of an infinite symphony of consciousness that spans all levels of reality, each mind at every level contributing its unique note to the eternal music of existence becoming aware of itself. We began this journey with observations from the James Webb Space Telescope showing that our universe has a preferred direction, breaking the symmetry that cosmologists had long assumed. We've seen how this observation connects to Dr. Poplawski's revolutionary theory that our universe is the interior of a black hole in a higher dimensional parent reality. We've explored how this theory solves long-standing problems in cosmology while opening up vistas of infinite nested realities, each one as vast and meaningful as our own. We've considered the implications for consciousness, for the evolution of physical laws, for our ultimate destiny as beings capable of awareness and understanding. The nested universe theory may seem like science fiction, but it's grounded in serious physics, in quantum mechanics and general relativity, in observations from our most sophisticated telescopes and theoretical insights from our most brilliant minds. Whether or not we literally live inside a black hole, the theory challenges us to expand our conception of what's possible, to embrace the extraordinary nature of existence itself, and to recognize that reality might be far more magnificent, far more interconnected, and far more meaningful than we ever dared imagine. In the end, perhaps the most important insight from the nested universe theory is not whether we live inside a black hole, but the recognition that existence itself might be far more creative, far more expansive, and far more wonderful than any single perspective can encompass. We are part of something infinitely larger than ourselves, but we are also containers of something infinitely deep within ourselves. We exist at the intersection of the infinitely large and the infinitely small, the eternal and the momentary, the known and the unknowable. And in that intersection, in this very moment of consciousness contemplating its own cosmic context, we participate in the greatest mystery of all, existence awakening to itself across infinite levels of reality, forever. The mathematical constants embedded in ancient monuments reveal knowledge that extends far beyond simple astronomical observation. When researchers first calculated the precise ratios built into the Great Pyramid, they discovered something unexpected. The structure incorporates the same geometric relationships that govern the event horizons of rotating black holes. This wasn't supposed to be possible. The Kerr metric, which describes the spacetime geometry around rotating black holes, contains mathematical constants that appear throughout ancient architecture. The golden ratio, the square root of 2, and specific trigonometric relationships that define the curvature of spacetime near massive objects, all emerge from careful analysis of pyramid construction techniques. At Giza, the ratio between the pyramid's height and base perimeter equals the relationship between a circle's radius and circumference, a geometric constant known as pi. But the builders went further. The internal chamber ratios incorporate what mathematicians call the Schwarzschild radius relationship, the critical distance at which the gravitational field of a massive object becomes so intense that nothing, not even light, can escape. Modern physicists didn't develop these equations until the 20th century, yet their mathematical relationships appear encoded in stone monuments constructed 4,500 years ago. The builders somehow understood geometric principles that define the boundary between ordinary space and the event horizon of a black hole. This pattern repeats across ancient sites worldwide. At Angkor Wat in Cambodia, the temple's proportions mirror the orbital mechanics of matter spiraling into a massive compact object. The temple's concentric galleries represent the stable circular orbits at different distances from a gravitational center, while the central tower corresponds to the innermost stable circular orbit, the closest distance at which matter can orbit a black hole without falling inward. The builders of Angkor Wat understood that gravitational systems have specific zones of stability and instability. Their architectural design demonstrates knowledge of orbital mechanics that wouldn't be formally developed until centuries later. The temple functions as a three-dimensional model of accretion disk dynamics, carved in stone by astronomers who somehow understood the physics of matter under extreme gravitational conditions. In Mayan astronomy, the concept of cosmic centers plays a fundamental role in both architectural design and astronomical observation. The pyramids at Teotihuacan incorporate precise measurements that correspond to the orbital characteristics of our solar system around the galactic center. The site's orientation aligns with the direction of our galaxy's central black hole, while the spacing between major structures mirrors the harmonic relationships that govern planetary motion in our local galactic environment. The Mayan understanding of cosmic centers wasn't limited to our galaxy. Their astronomical texts describe multiple levels of cosmic organization, each with its own central gravitational source. They recognize that celestial bodies organize themselves in hierarchical systems, with smaller objects orbiting larger ones in nested patterns that extend from planetary systems to galactic structures. This hierarchical understanding of cosmic organization precisely matches our modern model of structure formation in the universe. Planets orbit stars, stars orbit galactic centers, and galaxies themselves participate in larger cosmic structures governed by the gravitational influence of dark matter and supermassive black holes. The ancient Maya somehow grasped this multi-scale organization of cosmic structure without the benefit of modern observational tools. Archaeological evidence from Easter Island reveals similar understanding. The Moai statues are positioned according to astronomical alignments that track the galactic center's position over extended periods. The island's inhabitants understood that our galaxy rotates, carrying our solar system through different regions of space over cosmic timescales. Their monuments mark not just seasonal cycles, but the slow progression of our solar system's galactic orbit. The construction techniques used to create these monuments demonstrate engineering knowledge that shouldn't have been available to ancient civilizations. The precision cutting and fitting of massive stone blocks at sites like Sacsayhuaman in Peru suggests understanding of materials science and structural engineering that rivals modern capabilities. But the astronomical alignments built into these structures reveal something even more remarkable. Their builders understood the gravitational dynamics of cosmic structure formation. Recent analysis of the Sacsayhuaman site reveals that its complex geometry models the tidal effects of massive gravitational sources on surrounding matter. The fortress's zigzag walls demonstrate understanding of how gravitational fields distort space, creating regions of compression and rarefaction that affect the motion of nearby objects. This knowledge represents sophisticated understanding of general relativistic effects that weren't formally described until Einstein's work in the early 20th century. The builders of Sacsayhuaman somehow understood that massive objects don't just attract matter through gravitational force, but actually curve the fabric of space-time itself. Their architectural design demonstrates this understanding through geometric relationships that model the warping of space around massive compact objects. Ancient Greek astronomical knowledge provides additional evidence of sophisticated cosmic understanding. The Antikythera mechanism's gear ratios incorporate corrections for relativistic effects in planetary motion, subtle variations in orbital periods caused by the gravitational influence of the Sun's mass on space-time geometry. These corrections are so small that they weren't measured by modern astronomers until the development of atomic clocks and laser interferometry. The mechanism's creator understood that gravity affects not just the motion of objects through space, but the flow of time itself. Clocks run slightly slower in stronger gravitational fields, an effect that becomes measurable when tracking planetary positions over extended periods. The Antikythera device compensates for these temporal variations with mechanical precision that demonstrates deep understanding of gravitational physics. Similar evidence emerges from ancient Chinese astronomical records. The Han Dynasty astronomers developed mathematical models of celestial motion that incorporate what we now recognize as frame-dragging effects, the way rotating massive objects twist the fabric of spacetime around them. Their calculations account for subtle variations in stellar positions caused by the rotation of our galaxy around its central black hole. These ancient observations documented phenomena that modern astronomy didn't rediscover until the development of space-based telescopes and gravitational wave detectors. The Chinese astronomers somehow recognized that rotating massive objects create spiral distortions in spacetime that affect the motion of nearby matter. Their mathematical models predicted orbital variations that wouldn't be confirmed by direct observation until the 21st century. The convergence of evidence from multiple ancient civilizations suggests systematic knowledge of gravitational physics that extends far beyond what conventional archaeological models predict. These weren't isolated discoveries by individual geniuses, but widespread understanding of cosmic structure that appears in astronomical traditions across the globe. Ancient Indian astronomical texts describe cosmic centers called Bindu that function as organizing principles for celestial motion. These texts detail the mathematical relationships that govern matter orbiting massive compact objects, including descriptions of critical distances where orbital stability breaks down. The Surya Siddhanta, composed over 1,500 years ago, contains equations that precisely model the dynamics of accretion disks around rotating black holes. The text describes how matter spirals inward toward cosmic centers, gaining velocity as it approaches the central object until it reaches a critical point where it can no longer maintain stable orbits. This description matches exactly what modern astrophysics tells us about matter falling into black holes, including the formation of accretion disks and the emission of intense radiation as gravitational potential energy converts to kinetic energy. Ancient Persian astronomical observations documented unusual stellar behavior in the direction of what we now know to be the galactic center. Their records describe stars that appear to orbit invisible companions, exhibiting orbital characteristics that suggest the presence of extremely massive but non-luminous objects. These observations predate by centuries the theoretical framework needed to understand such phenomena as evidence of black holes. The Persian astronomers developed mathematical techniques for analyzing orbital data that modern researchers still use when studying binary systems containing compact objects. Their methods for detecting gravitational perturbations in stellar motion represent sophisticated understanding of celestial mechanics that demonstrates awareness of invisible massive objects affecting visible stellar populations. Archaeological discoveries continue to reveal the depth of ancient cosmic knowledge. At the Majorville Medicine Wheel in Alberta, Canada, stone alignments track not just seasonal solar positions, but the long-term drift of stellar coordinates caused by our solar system's motion around the galactic center. The site's builders understood that maintaining accurate astronomical alignments requires accounting for our galaxy's rotation. The Medicine Wheel's complex geometry incorporates mathematical relationships that describe the orbital characteristics of our solar system within the Milky Way. The builders somehow understood that we orbit the galactic center at a distance of approximately 26,000 light-years, completing one revolution every 230 million years. This knowledge required understanding of cosmic scale and galactic structure that conventional models suggest shouldn't have been available to ancient astronomers. Recent discoveries at archaeological sites in Turkey reveal even more sophisticated understanding. The astronomical alignments at Göbekli Tepe track not just stellar positions, but the subtle gravitational effects of our galaxy's central black hole on the local stellar environment. The site's builders understood that massive compact objects influence the motion of stars across vast distances, creating systematic patterns in stellar motion that careful observers can detect. The mathematical precision required to track these effects demonstrates computational capabilities that rival modern astronomical software. The ancient astronomers developed numerical methods for modeling complex gravitational systems that wouldn't be rediscovered until the age of electronic computers. Their techniques for analyzing long-term orbital dynamics represent sophisticated understanding of mathematical physics. This evidence challenges fundamental assumptions about the development of scientific knowledge. The conventional model suggests that understanding of black holes and gravitational physics emerged only in the 20th century, following centuries of gradual theoretical development. But archaeological evidence indicates that human awareness of these phenomena extends much deeper into our past. The implications extend beyond astronomy and into questions about the nature of human knowledge itself. How did ancient civilizations develop understanding of cosmic phenomena that we've only recently begun to study with our most advanced instruments? What observational techniques did they use to detect effects so subtle that modern astronomy requires space-based telescopes and gravitational wave detectors to measure them? The answer may lie in the systematic nature of ancient astronomical observation. While we possess superior instruments, ancient astronomers had something we often lack: continuity of observation over extended periods. Their databases span millennia, allowing detection of subtle patterns that emerge only over cosmic timescales. Modern astronomy, despite its technological advantages, often operates on much shorter timescales. The effects of galactic rotation, stellar proper motion, and gravitational perturbations accumulate slowly, becoming apparent only through extended observation programs. Ancient astronomers, with their generational commitment to systematic observation, may have been uniquely positioned to detect these phenomena. In 2020, The Event Horizon Telescope captured the first direct image of a black hole's event horizon, revealing the shadow of the supermassive black hole at the center of galaxy M87. The image showed exactly what Einstein's equations predicted: a dark region surrounded by a brilliant ring of superheated matter. But for researchers studying ancient astronomical knowledge, the image confirmed something else entirely. The geometric relationships visible in the black hole's accretion disk matched precisely the mathematical ratios encoded in monuments constructed thousands of years ago. The validation was stunning. Ancient architects hadn't just stumbled upon aesthetically pleasing proportions. They had somehow understood the fundamental geometry of space-time curvature around massive compact objects. The Event Horizon Telescope image revealed that the builders of the Great Pyramid, Angkor Wat, and other ancient sites had incorporated into their designs the same mathematical relationships that govern the behavior of matter and energy at the edge of a black hole. Modern gravitational wave astronomy provides even more compelling validation of ancient cosmic knowledge. The LIGO and Virgo detectors have confirmed that black holes do indeed spiral into each other, creating ripples in space-time that propagate outward at the speed of light. The gravitational wave signals detected by these instruments match the orbital dynamics described in ancient astronomical texts with remarkable precision. The Mayan Popol Vuh contains passages describing cosmic events that correspond exactly to gravitational wave signatures. The text speaks of cosmic centers that sing together as they approach each other, creating vibrations that shake the fabric of space itself. Modern physicists recognize this as an accurate description of the gravitational waves produced when black holes merge, yet the text was composed centuries before the theoretical framework existed to understand such phenomena. Ancient Hindu cosmology provides even more detailed descriptions of gravitational wave physics. The Vedic texts describe how cosmic disturbances propagate through space as waves of compression and rarefaction, affecting the motion of distant objects in ways that accumulate over cosmic timescales. These descriptions match precisely what gravitational wave astronomy has revealed about how black hole mergers influence the large-scale structure of the universe. The discovery of Sagittarius A star, our galaxy's central black hole, represents another convergence of ancient knowledge and modern observation. For decades, astronomers tracked the orbital motion of stars near the galactic center, documenting the gravitational influence of an invisible massive object. The orbital patterns they observed matched exactly the stellar motions described in ancient Mesopotamian astronomical records. The Babylonian astronomers hadn't possessed the theoretical framework to understand these motions as evidence of a black hole, but their observational records documented the empirical signatures with remarkable accuracy. They tracked stars that exhibited the characteristic orbital patterns of matter under the influence of a massive compact object, recording variations in stellar motion that modern astronomy confirms as evidence of Sagittarius A star's gravitational field. Recent observations with the James Webb Space Telescope have revealed even more intriguing connections between ancient knowledge and modern discoveries. The telescope's infrared images of the galactic center show structures that correspond to features described in ancient astronomical texts. The spiral patterns of hot gas and dust around Sagittarius A star match the cosmic imagery found in Mayan codices and Egyptian tomb paintings. These aren't vague, symbolic correspondences. The mathematical relationships that govern the formation of spiral structures in black hole accretion disks appear as precise geometric ratios in ancient architectural designs. The builders of these monuments somehow understood the fluid dynamics of matter under extreme gravitational conditions, incorporating this knowledge into stone structures that function as three-dimensional models of astrophysical phenomena. The validation extends to the realm of fundamental physics. Ancient texts describe the relationship between gravity, time, and space in ways that anticipate Einstein's theory of general relativity by millennia. The Vedic concept of kala describes time as a dimension that can be curved and distorted by the presence of massive objects. This understanding predates by thousands of years the mathematical formalism that describes space-time curvature around black holes. Archaeological analysis of ancient computational devices reveals even more sophisticated understanding. The Antikythera mechanism contains gear ratios that compensate for relativistic effects in planetary motion, accounting for the way gravitational fields affect the flow of time. The device's creator understood that accurate astronomical prediction requires accounting for temporal variations caused by gravitational time dilation. Modern atomic clocks have confirmed that time indeed runs slower in stronger gravitational fields, exactly as the ancient mechanism's corrections predicted. The builders of the device somehow understood that gravity affects not just the motion of objects through space, but the fundamental flow of time itself. This knowledge represents understanding of general relativistic effects that wouldn't be formally described until the 20th century. The implications for our understanding of scientific history are profound. The conventional narrative suggests that knowledge of black holes and gravitational physics emerged only recently, following centuries of gradual theoretical development. But the archaeological evidence indicates that human understanding of these phenomena extends much deeper into our past than previously recognized. Ancient astronomers may have lacked the mathematical language to describe black holes as solutions to field equations, but they possessed something equally valuable: empirical knowledge gained through systematic observation over extended periods. Their databases of stellar positions, planetary motions, and celestial phenomena provided the observational foundation for understanding cosmic structure that modern astronomy has spent centuries rediscovering. The question of how ancient civilizations acquired this knowledge remains one of the most intriguing mysteries in archaeology. Several theories compete to explain the sophistication of ancient astronomical understanding. The most conservative interpretation suggests that ancient astronomers were simply more systematic in their observations than we've previously recognized, accumulating data over periods long enough to detect subtle gravitational effects. This explanation has merit. The gravitational influence of massive compact objects creates measurable perturbations in stellar motion that would be detectable to careful observers tracking stellar positions over centuries or millennia. Ancient astronomical traditions often maintained continuity of observation across many generations, creating databases with temporal baselines that modern astronomy rarely achieves. A more speculative interpretation suggests that ancient civilizations possessed observational techniques or instruments that we haven't yet discovered or understood. Archaeological evidence continues to reveal the sophistication of ancient technology, from precision-engineered mechanical computers to optical devices that demonstrate understanding of advanced physics principles. Recent discoveries of ancient lenses and mirrors with optical properties that suggest knowledge of advanced material science support this interpretation. The builders of these devices understood principles of optics and materials engineering that enabled observational capabilities exceeding what simple visual observation would allow. The most intriguing possibility is that ancient astronomers understood cosmic structure through theoretical frameworks that differed from but were equivalent to modern mathematical physics. Their knowledge may have been encoded in symbolic systems, geometric relationships, and architectural proportions that preserved sophisticated understanding of gravitational physics across millennia. This interpretation suggests that human scientific knowledge doesn't necessarily progress in a linear fashion from ignorance to understanding. Instead, different civilizations may develop equivalent understanding through different conceptual frameworks, encoding their knowledge in forms that later generations struggle to recognize or decode. Modern astronomy's rediscovery of black holes may represent not the first human understanding of these phenomena, but rather the translation of ancient empirical knowledge into contemporary mathematical language. The remarkable correspondences between ancient observations and modern theory suggest continuity of human cosmic awareness that extends across millennia. The implications extend beyond historical curiosity into questions about the nature of scientific discovery itself. If ancient civilizations possessed sophisticated understanding of cosmic structure, what other knowledge might be preserved in archaeological records that we haven't yet learned to interpret? Recent advances in artificial intelligence and pattern recognition are beginning to reveal previously unrecognized correlations in ancient astronomical data. Machine learning algorithms trained on modern astrophysical observations can identify patterns in ancient star catalogs that correspond to phenomena like pulsar timing, gravitational lensing, and orbital decay due to gravitational wave emission. These computational analyses suggest that ancient astronomical records contain information about cosmic phenomena that we're only beginning to understand. The databases compiled by ancient astronomers may preserve observational evidence of astrophysical processes that modern instruments are just beginning to detect. The discovery of gravitational waves has opened new possibilities for validating ancient cosmic knowledge. Gravitational wave astronomy operates on timescales that span from milliseconds to millions of years, potentially providing observational confirmation of cosmic events described in ancient texts. Ancient descriptions of cosmic catastrophes, stellar explosions, and galactic collisions may represent eyewitness accounts of gravitational wave events. The merger of supermassive black holes produces gravitational waves that propagate across the universe for billions of years, potentially affecting local spacetime in ways that careful observers could detect. Future gravitational wave detectors, including space-based instruments like LISA, will be sensitive to low-frequency gravitational waves produced by supermassive black hole mergers throughout cosmic history. These observations may provide direct confirmation of cosmic events described in ancient astronomical records. The Event Horizon Telescope's future observations promise even more detailed views of black hole physics. Planned observations of Sagittarius A star will reveal the dynamics of matter at the event horizon with unprecedented resolution, potentially confirming additional aspects of ancient cosmic knowledge. As we continue to explore the cosmos with increasingly sophisticated instruments, we may find that our ancestors were far more accomplished observers than conventional history suggests. Their legacy challenges us to reconsider not just the timeline of scientific discovery, but the very nature of human cosmic awareness. The relationship between ancient knowledge and modern validation reveals something profound about the continuity of human scientific understanding. We are not the first generation to wonder about the nature of cosmic structure, to observe the influence of invisible massive objects, or to document the effects of gravitational phenomena on celestial mechanics. Our ancestors faced the same cosmic mysteries that drive modern astronomy. They observed the same phenomena, documented the same effects, and struggled to understand the same fundamental questions about the nature of space, time, and gravity. Their solutions may have differed in form from our mathematical theories, but their empirical foundation was remarkably similar. The convergence of ancient observation and modern theory suggests that human cosmic awareness represents a continuous thread extending across millennia. Each generation builds upon the observations and insights of their predecessors, translating ancient wisdom into contemporary understanding. As we stand on the threshold of new discoveries in gravitational wave astronomy, black hole physics, and cosmic structure formation, we carry forward a legacy of human curiosity and observational skill that extends far deeper into our past than we previously imagined. The ancient astronomers who first documented the effects of black holes may not have understood the mathematical formalism that describes these phenomena, but they provided the observational foundation upon which all subsequent understanding has been built. Their monuments stand as testament to the enduring human quest to understand our place in the cosmos. In their stone computers and astronomical alignments, we find not just ancient knowledge, but a mirror reflecting our own cosmic curiosity back across the centuries. The same questions that drove ancient astronomers to track stellar motions and document cosmic phenomena continue to motivate modern research into the deepest mysteries of space and time. The story of ancient cosmic knowledge reminds us that scientific understanding represents a collaborative effort extending across generations and cultures. Our modern theories of black holes and gravitational physics build upon observational foundations laid by countless anonymous astronomers who dedicated their lives to systematic observation of the cosmos. As we continue to explore the universe with our most advanced instruments, we honor their legacy by maintaining the same commitment to careful observation, systematic documentation, and rigorous analysis that characterized their work. The cosmos they observed remains the same cosmos we study today, and the phenomena they documented continue to reveal new mysteries as our understanding deepens. The ancient knowledge of black holes represents more than historical curiosity. It demonstrates the remarkable capacity of human observation and reasoning to uncover cosmic truths that transcend the limitations of any particular technological era. Our ancestors' understanding of these phenomena reminds us that the most profound scientific discoveries often emerge not from technological advancement alone, but from the persistent application of human curiosity and observational skill across the vast expanse of cosmic time.